Welcome to our lecture online, and here we're going to do an interesting problem with pulleys. Now before, when we worked with pulleys, we ignored the mass of the pulley. And so we assumed that as masses went up and down as they're connected with a string going over a pulley, that the pulley had no play or no say in what happens to the rest of the system. But in this case, we're going to look at a more realistic system with a pulley that actually has mass. So therefore, the pulley will have a moment of inertia, and therefore, as things begin to rotate and the masses begin to go up and down, energy will be stored in the rotation of the pulley. So, if a question like this comes along that says, what will be the velocity of the 10 kilogram mass when it strikes the floor, we have to take into account that the pulley will also have some play in this formula and will have some impact on the velocities of the masses. So we still start with the very same equation as before, that energy initial equals energy final. And so we can say that the work input into the system plus the initial potential energy plus the initial kinetic energy must equal to the final potential energy plus final kinetic energy plus any heat lost in the friction. Now, which of these are zero? Well, let's say we set up the system, we hold it in place, and then we let go the moment time equals zero. That means there's no work input to the system, and we can set that equal to zero. Also, no mention of friction was made, so therefore we can assume that there's no heat loss due to friction. And since everything starts from rest, the system will have no kinetic energy at the very beginning, so that will also be zero. So what then happens to this equation is that the initial potential energy of the system must equal the final potential energy of the system plus any kinetic energy of the system. So part of its initial potential energy went into kinetic energy, the remainder stayed as potential energy. So let's define then what everything is before the system starts moving. So assuming that h equals 0 is at the ground, and we can see that the mass 2 is at the ground at the start, the only potential energy is due to the height of mass 1. So we can say that m1gh is the potential energy into the system. That potential energy will cause the system to start moving and will cause m2 to go up as m1 goes down. The final potential energy when m1 strikes the ground is when m2 is at the height of m1 at the beginning of the problem. So we can say that the potential energy final will be m2gh, because m1 will now be on the ground, m2 will be 4 meters higher than it started. And then the kinetic energy of the system will be wrapped up in the kinetic energy of m1 plus the kinetic energy of m2 plus the kinetic energy stored in the rotation of the pulley. So that will then be plus 1/2 m1 v squared, whatever the velocity was of that mass when it strikes the ground, which is, by the way, what we are trying to find, right? What is the velocity of the 10 kilogram mass? So v equals question mark, that's the velocity we're looking for. Of course, m2 will be moving up at that same velocity, so that also has kinetic energy, 1/2 m2 v squared. The velocities, of course, will be equal. And then finally, we have kinetic energy in the rotation of the wheel, and so that would be plus 1/2 I omega squared. That is the rotational form of the kinetic energy which the pulley will have. Now remember, since this is a pulley and we can assume that it's a solid disk, that the I will be equal to 1/2 m of the pulley omega squared. Oh, not omega squared, I'm getting ahead of myself, is mass of the pulley times the radius squared. That's the moment of inertia of the pulley. And then relating omega to velocity, we know that the tangential velocity along the pulley will be equal to r times omega, or omega will be equal to v over r. So replacing omega by v over r, replacing I by 1/2 mp r squared, this equation now becomes m1gh equals m2gh plus 1/2 m1 v squared plus 1/2 m2 v squared plus 1/2 times, instead of I, we're going to write 1/2 mass of the pulley times the radius of the pulley squared. Okay, that's the moment of inertia of the pulley, times omega squared, which is v squared over r. Like that. And now right away we can see that this r squared cancels out this r because this r will be squared as well. And now simplifying things a little bit more, we can say that m1gh equals m2gh plus 1/2 m1v squared plus 1/2 m2v squared, and then plus 1/4 the mass of the pulley times v squared. And ultimately, remember, we are looking for v squared, so this term has a v squared in it, that term has a v squared in it, that term has a v squared in it. We now have to somehow isolate v squared. We can do that by moving the m2gh to the other side of the equation and factoring out a v squared from the right side of the equation. So then what we get here is m1gh minus m2gh equals v squared times 1/2 m1 plus 1/2 m2 plus 1/4 the mass of the pulley. Like so. I can then factor out a gh out of the left side of the equation, divide both sides by what's in the brackets, so we can isolate, and then I flip the equation around, so I can say v squared is equal to what I have on the left side with gh factored out, so gh times m1 minus m2, divided by everything that's in the brackets, which would be 1/2 m1 plus 1/2 m2 plus 1/4 m of the pulley. And now I'm ready to go ahead and solve for v, realizing, of course, if I take the square root of both sides, I will know the velocity of the mass when it strikes the floor. All right, plugging in the numbers. This is equal to the square root of g, which is 9.8 meters per second squared. Multiply times h, and it started at a height of 4 meters. And multiply times the difference between the two masses of 10 kilograms minus 5 kilograms. So 10 kilograms minus 5 kilograms. Okay, that's the numerator. And I divide the whole thing by half mass 1 plus half mass 2 plus 1/4 the mass of the pulley. So that would be 1/2 times 10 kilograms plus 1/2 times 5 kilograms plus 1/4 times, let's see here, 2 kilograms. And what do we get? I guess before we work that out, so this will be equal to the square root of, that would be 9.8, make it a little bit bigger, 9.8 times 4 times 5 in the numerator. In the denominator, we have half a 10, that's 5, half a 5, that's 2.5, that's 7.5, and 1/4 of that would be another half, that would be 8, so divided by 8. And then, of course, the 4 and the 8, that goes 1, that becomes 2, and that becomes a relatively easy thing to follow, and that would be meters per second, of course, because we're dealing with velocities. Just makes it a little bit easier to work this out in a calculator. And so we have 9.8 times 5 divided by 2. And take the square root, and we get 4.95 meters per second. So v equals 4.95 meters per second. And there you go. Now, of course, the actual number in the answer isn't as important as long as we understand what we were doing. So let's quickly repeat what we're doing. We have a pulley system. We have a heavy mass and a small mass. The small mass is on the ground. The heavy mass is in the air, and we let things go. The pulley, of course, has mass, and if it has mass, it has a moment of inertia. So as things begin to move, we can assume that the initial energy that the system had, with the big mass being up here, equals the final energy that the system has with the big mass on the floor and the little mass up here, and everything moving just before the big mass strikes the floor, which means that the initial m1gh, the only energy that the system had when the big mass was up in the air, equals the total energy that the system has, which comes from the potential energy that the small mass has when it's in the air, m2gh, plus the kinetic energy of the moving big block, the moving small block, and the rotating wheel. The moving big block plus the moving small block plus the rotating wheel. Then, of course, you realize that I can be expressed as 1/2 mr squared because we think of it as a solid disk. And then we can also replace omega squared by v over r squared. That's the equivalent of the rotational velocity. Then eventually we see then in this case we have 3 terms that have the velocity term in there, the velocity component in there. Then we isolate the velocity and plug in the numbers. And that's how you do a problem like that.